All right, Sibel, we are going to go through a slant asymptote example from a rational function as you'd requested. Um, we have here rational function example. On the top is a cubic, x cubed plus 2x squared minus 5x plus 1, all of that over x squared minus 1. So if you recall, we know we have a candidate for a slant asymptote when the degree of the numerator is one higher or plus one over the degree of the denominator. So that means for this one, in other words, we're going to look at we got a 3 here for the cubed, we got a 2 here. So that puts us right in the category of having the slant asymptote. So we can move forward then with this, with either synthetic division or polynomial long division. That's polynomial long division is what you have been doing. So we will go ahead and do that. And let's go ahead and set it up here. We've got x squared minus 1. And we're dividing it into the top, x cubed plus 2x squared minus 5x plus 1. So remember, the first thing we're looking at in this long division, we're focused on this lead term in the divisor, and what we need to multiply that by to get to the first lead term, in this case x cubed, to make that the lead term. Well, we would need to multiply x squared by x to get x cubed, right? So we're going to put that x right above the x term, the other side of the division bar. What do we do from there? Well, we're going to then carry through that multiplication. That is x cubed. X times x squared is x cubed. We're also going to say, oh, let's multiply that x by negative 1. So both of those in the divisor. So x times negative 1 is a negative 1x. Well, we want to put the x term underneath the x term in the dividend, the negative 5x. Because when we subtract the difference, we need it to be in that column conveniently. So what do we do with this term here? Well, technically, what about this guy right here? What happens? Well, technically, we'd have within this x squared plus 0x minus 1, right? And we could write that down if we wanted to, either have it understood in our mind or write it down. So we have a 0x in there. We have a 0x. So if we had x times a 0x, that's between these two, right? We'd have a 0x squared. So we can either multiply it through by including the 0x term there, or just know that, well, the x squared term is involved. We're just going to use it as a placeholder, use 0x squared, because when we do that, then when we subtract the difference here, we know this is 0 here, right? X squared, x cubed minus x cubed, 0. 2x squared minus a 0x squared is a positive 2x squared, right? 2 minus 0, 2. Negative 5 minus a negative 1, or in other words, negative 5 minus a minus, so plus 1, that's going to be a minus 4x or negative 4x. And then we're going to carry on down that 1. He gets to be involved now too. Okay. So now we have 2x squared minus 4x plus 1 as a dividend. We're going to divide into that x squared minus 1. So again, lead term, x squared 2x squared. What do I need to multiply x squared by to get a positive 2x squared? Well, that would be a positive 2. We're going to multiply it again. 2 times x squared, we said is 2x squared. 2 times, remember, a 0x is a 0x. And 2 times -1, that is a -2. Subtract that difference now. Put the parentheses around because you want to make sure we're not missing anything with our format, with our signs, I should say. 2x squared minus 2x squared, that's 0. -4x minus 0x is a negative or minus 4x. Positive 1 minus a -1, or in other words, minus a minus, that's going to be a plus 3, right? It's a positive 1 plus 2 is a plus 3. So this now is, we don't have anything to bring down, right? We can't bring anything else down. We're done with what's in this term, or this polynomial here. So this becomes our remainder. We add this on to the quotient. Plus, and how do we write that? Well, it's, or we could technically put a minus because we have a negative here, but we'll say -4x plus 3. Remember, this is our remainder. Over what? Over x squared minus 1. We're going to include that. That is included in the remainder. So this is our remainder portion. This is the quotient, and then added on to that is the remainder portion. So what do we do with this? Well, to identify, because we want to identify the oblique asymptote here. We know it is because we have a degree higher, 1 higher than the denominator, from the numerator to denominator. The quotient is the oblique asymptote. So this quotient is the oblique asymptote, and to see how it performs, we need to first, or how it behaves, we need to first determine with the remainder what's happening as x goes to positive or negative infinity for that guy. So -4x. So in the remainder, we're now determining what happens as that goes to positive, negative infinity. Because, and we'll see it in the graph, and let's just show our hand a little bit here. This is what that rational function looks like graphed. So I went ahead, got into Desmos, put it in. So this is what it looks like graphed. So as this goes to the positive infinity x direction, negative infinity x direction, it's going off and doing something. Something's going on here. And we want to know in those directions what's happening when in regards to the remainder. Well, if I have this go to, let's just say positive infinity, I'd have positive infinity, and in fact, technically a positive infinity plus 3, and this would be positive infinity squared minus 1. That might be a little hard to determine. Okay, I don't really know the behavior that's going on. What I could do is say really high number to represent, infinity. So we'll say, like, what's a pretty high number? Like 1 million? What if we said 1 million times -4 plus 3? Plus 3 is not really do anything, right? It's just adding 3 to -400 million. And then what about this? 1 million squared minus 1. Well, again, the plus 3, like this, the minus 1 really doesn't drive anything. It's what's going on in this x squared term, right? Well, between the two, what's going to be higher? Well, this guy is. This guy is because why? Because you have this square term. 1 million times 1 million is a lot more. You can punch it in if you want, but it's a lot more than 1 million times -4. So you have a fairly sizable number over a really sizable number, right? So in general, what would we say the behavior is to this of this? Well, it would be going if I have a really high number, the denominator compared to the numerator, it's going to be 0. You divide something by a really big number, much bigger than the numerator, it's going to be going to 0. So therefore I can say, this function behaves like this: x plus 2. That's this guy here when I'm talking about that function here. This x plus 2 plus 0 as we're going to infinity, positive, negative infinity. That we have this going on, or in other words, just x plus 2. So that quotient, that's how that's behaving there. When I go to negative and positive infinity, it's going to 0 for that remainder portion. So x plus 2 plus 0. And that then is our slant asymptote. How are we sure? Are we sure about that? Well, let's take a look at Desmos. Let's look at that graph. As you see here, I have y equals x plus 2. So it's a linear function. That's the quotient we got. Check out how this overlaps. I'm going to click on that. As you can see, this blue line is x plus 2. Where is that shaping up to be? Right near, almost on. Even at -20, it looks like it's almost on, but it's not on. It can't touch it. It cannot touch it because it's an asymptote. That is, the red can't touch that blue.